Welcome. So for the longest time, we kind of had this picture of how planets form, right? Sort of a slow, quiet process.
Yeah, exactly. Young star forms, and there's this leftover cloud of gas and dust, the protoplanetary disk.
And planets just gradually clump together in there.
Yeah,
Nice and neat.
that was the thinking. But recent observations have really shaken that up.
You mean with Alame, the Atacama Large Millimeter Submillimeter Array?
Precisely. We've gotten these incredible close-up looks at well over 100 of these disks now.
And they're not the smooth, peaceful clouds we imagined.
Not at all. They're complex, dynamic structures, full of gaps, rings, things happening.
Which suggests planet formation might kick off much, much earlier. And maybe faster.
That's what it looks like. Things are moving quicker than the old model suggested.
Okay, that brings up a puzzle, doesn't it? Especially with massive stars.
Yes, the paradox.
They have these huge protoplanetary disks, massive amounts of material. You'd think intuitively more planets, right?
Logically, yes. More raw material should mean more planets, or bigger ones.
But these massive stars, they live fast and die young, relatively speaking.
Exactly. They burn through their fuel so quickly, there's seemingly less time for that slow, quiet planet formation process we used to imagine.
So, big disk, but short lifespan. How do planets manage to form around them? It feels contradictory.
It does. And that's pushing us to rethink fundamentally what these disks are. Maybe they aren't just leftovers.
Not just leftovers. What else could they be? Are they being topped up?
That's the radical new idea gaining traction. That young stars continue to actively pull in material from their surroundings.
Like even after the star itself has ignited.
Yes. Through a process called Bondi-Hoyle accretion, the star's gravity keeps drawing in nearby gas.
Okay, so the star keeps feeding, but how does that help build planets in the disk? Wouldn't the star just swallow it all?
Well, here's the twist. The new theory suggests, and simulations seem to support this, that the star doesn't actually accrete all of it smoothly.
It's messy.
You can say that. Some of the material falling towards the star gets, well, sort of spat back out into the disk.
Spat back out, seriously. Like it overeats and burps?
Uh-huh. Maybe not quite like that. But yes, some material is ejected back, enriching and, crucially, stirring the disk.
So the star is actively shaping its own planet-forming environment, not just passively sitting there.
That's the emerging picture. It's a much more turbulent, active process. The star is feeding, yes, but also feeding the disk itself in a way.
And this helps explain the paradox.
It seems to. Computer simulations of this turbulent feeding show it can sustain these large disks for longer, even around massive stars. It explains their size and apparent longevity better than the simple leftover model.
It provides more material, maybe, and keeps things mixed up for planet formation.
Exactly. It potentially extends the window for planet building, even with the star's shorter lifespan.
But can we see this happening, this feeding and spitting back?
Well, that's the tricky part. A lot of this action, these streams of gas flowing in, these dense filaments, they're likely invisible to our current telescopes.
So there's a hidden flow, a whole dynamic process we're not directly observing yet.
Pretty much. We see the effects on the disk, the gaps, the turbulence, but not necessarily the underlying engine driving it all. This hidden flow seems crucial.
Wow. Okay, so the whole picture is shifting. It's not a calm nursery. It's more like an active construction zone being constantly supplied and reshaped by the star itself.
That's a good way to put it. From passive leftovers to an actively fed and sculpted environment.
And this resolves the issue with massive stars, because the disk is being replenished, giving planets more time or material to form, despite the star's short life.
It provides a strong mechanism for it, yes. The disk isn't just dwindling away, it's part of a dynamic inflow-outflow system connected to the star.
So what's next? How do we actually see this hidden flow?
That's where future tech comes in. More powerful supercomputers for even better simulations, and next-generation telescopes.
Like the Giant Magellan Telescope or others.
Exactly. Instruments like GMT might just have the power and resolution to potentially detect these faint inflowing streams of gas directly.
That would be incredible, to actually see the star feeding its disk.
It would be a huge step forward in understanding how, stars and their planets are truly born.
It really changes the narrative. So here's something to think about. If planetary systems have such a dynamic, actively shaped beginning, rather than just forming from passive leftovers, could that mean we need to rewrite the origin story for, well, potentially even our own solar system? What does that early turbulence imply for the planets we see today?